me start thanking Inigo and all of you. Thank you, Inigo, for this way out type of presentation. You divide that by, take the square root of that, and it's closer to reality probably. And thank you for the invitation to be here today. It's really a great pleasure to come back to Cantabria, and for my grandparents migrated from here to Venezuela, in fact, many, many years ago. And besides, a place where I have many friends and very, very strong type of ties for many, many reasons. Thank you again, Igor. Thank you to all of you. And my topic today, I think, is half an hour, right? Very good. Is this one, the title is that one, Hydrology and Biodiversity. And, you know, I will not spend much time trying to, trying to motivate the topic of biodiversity. It's all over the place. You know, you read the papers nowadays, and one of the big things is biodiversity and biodiversity. I could spend a lot of time talking about the value, the practical value of biodiversity in the sense of things like, for example, all the ecosystem services that we all worry about are highly dependent on biodiversity. The amount, for example, of fish biomass in largest fish systems like the Mekong River Delta, et cetera, are dependent on biodiversity. And they interact with engineering problems. You know, when you build dams right now, it's very much on the table. The whole development of the Mekong River Delta, and with many, many dams. I will not get into the details of that. We just published a paper in PNAS, Proceedings National Academy of Science, about that. It was a practical oriented paper, which dams will impact the biodiversity and which will not, which ones will impact the total biomass of fish in the system and which will not. And as I say, it has a lot of practical implications. It also has a strong content of what I call intrinsic beauty, which is really, at the end of the day, what motivates many researchers. Is a problem which is beautiful by itself to study. And one of the links that biodiversity, I think, has, and very strong one, and not very much pursued, and there is a lot to do that in terms of research, exciting research, is the link of biodiversity with hydrologic dynamics. Hydrologic dynamics both in terms of things like the hydrologic inputs like rainfall, stream flow, soil moisture, etc., but also hydrologic dynamics in terms of its links, biodiversity in terms of the links with the drainage network of rivers, the issue of connectivity, which is the one, for example, that impacts so dramatically the problem when you build dams. And by one, I am not one that is, you know, that sustain no more dams at all ever. And come on, there are good dams and there are bad dams, and I'm willing to argue that in front of everyone. So I am not in that extreme of things. I think it's silly to maintain that the dams are, you know, the work of the devil, and they should be excluded from, no. But in the other hand, there are dams that are extremely prejudicial. I mean, they really cause troubles. But we need a framework to establish the plus and minus of all these things. This framework has to be based in solid science. That's what that publication, I think, is the first one really that provides a framework to analyze, for good or for bad, I hope for good, objectives that are not very easily commensurable or non-commensurable at all, like biodiversity and energy production and things like this. Has to do a lot of it with equilibrium, you know, Nash point of equilibrium, for those familiar with economics type of theories, et cetera, et cetera. But it has to be based in solid science. So one of the things that I want to stress here is the beauty of the topic. And let me start with the connectivity issue. You see, connectivity rules, is what somebody says regarding to this topic. You see, it's not. We will go later on to trees, vegetation. But if you think in fish, it's very easy to see. I mean, the fish cannot get out of the network. They have to be in the water, in the river network. So they go from one place to another via the network. The structure of the network then controls a lot, or fundamentally controls, not only the capacity of the habitat capacity of how many fish can live there, you know, happily, et cetera, et cetera, et cetera. The population capacity of each link of the river, that's the flow itself, you know, it's controlled by the flow. But also the network, the connectivity of the network links one place with every other place in the network. In fact, fish can and do, in fact, travel upstream. There is a difference between upstream and downstream. But it's the network itself, the one that controls very, very much this connectivity, and at the end of the day, controls a lot the biodiversity. In this case of fish, I'm just using fish as an example. And the network has been, it's a thing again of intrinsic beauty, the network of a river. And I always say that one of the things that I would have loved to have someone pointed out to me when I was starting in hydrology was precisely that fact, to ask the fundamental questions. I'm talking a lot in front of young people. So, I want to encourage you to ask the difficult questions that sometimes sound extremely naive, but are extremely difficult to solve, at least solve in a general manner and quantitative manner. Ask a professor of hydrology, why in Earth do river networks are networks like that? Let me see, like this. Why? Why does nature like this type of a structure? That is very common in nature. It's also common, say, in trees. It's also common in the lungs. In the lungs, it's a bit different because it has loops. The drainage network and the river network classically doesn't have loops. If you look at a delta, it's similar to this, but with a lot of loops. Why in some cases nature uses loops, and in some other cases does not use loops? Why this only exists in the production zone, in the river network itself, and after that river kind of meanders slowly and so on? Why those differences? Why nature works that way? Those are very, very key questions that are at the root of problems like this. It's very easy to talk in general about the beauty of biodiversity, which in fact is true, and the needs for it, et cetera, and it's also a very different thing to say, I'm going to link this structure to the problems of biodiversity. To do that, you have to start by knowing why in Earth this structure is like it is, and what are the general rules that control the shape of this structure. Are there general rules? Yes, there are. There very much are. And every network of this kind, I don't care how different it looks to the eye, it has some fundamental unity on it that goes beyond the simple appearances. And that unity is where beauty in science lies. So I will not get into that because my topic is not river networks this time, but it's indeed a very fascinating topic and very much linked to this problem. Now, the importance of the topic, you can see it here. You see, this is a 2D lattice here, and this is two-dimensional lattice, and this is a red or whatever net. And here is the network itself, and it's very different. The type of biodiversity that you get. This is just a mathematical example in which we propagate some things. We were using the so-called Volter model, but forget about details, between this guy and this guy. So in here, there's a preferential movement in this direction. If it's fish, it always moves along the network. If it's not fish, there may be a preferential movement of the network, but there also be movement across the network. And that can be done mathematically. I mean, we can incorporate those mathematically. But I want to show you the example, how different it is. With the same thing, with something that we call the speciation rate, is how much a species change in time, or the input of new species in time, how different it looks, the result that you get when you have a 2D lattice with a network, with a preferential movement along the network, and the other one, everything is the same except the connectivity. And look at here, this network, in fact, is the same way here, that network, but the colors are different species. They look extremely different. Connectivity rules, in fact. And this is an example of a river in Oklahoma. This is Rashata Muneparakolos is a former doctoral student. He's now University of Arizona State, I'm sorry. And again, I just point this out for those starting in science or doing research, young people, is, I just put in here general theoretical biology. Nowadays, the boundaries of science are very diffuse. And you will find hydrologists working in biology issues and publishing in journals of theoretical biology, and vice versa. Simon Levine there is very, very well known here. Is a very well-known theoretical mathematical ecologist. And the other parts of the group here, we are all hydrologists. But this is a river basin in Oklahoma, and here are from space. I will not get into that. With data is available, thank God. A lot of data is available nowadays, and the different colors are different types of vegetation species and how they are distributed along the network. Again, riparian zones close to the network are extremely important. Now, riparian zones, how do they get there? Obviously, the network plays a very important role in what type of species you're going to have in one part or another, and they are related. Now, when you see this, the first thing that you say is, my goodness, I have to describe what type of a structure do I have in there regarding the different type of vegetations, and how are they linked to the network itself? That's a nice question to ask in a doctoral thesis. Can you do that? And then, okay, one of the things I will not get into the detail that comes out is that if you have to do it probabilistically, of course, the probability of the number of species in an extreme link, probability that the number of species in a extreme link is larger than a certain number versus the number, this is a probability, cumulative probability function, the complementary cumulative probability function in this case, and in many cases in riparian species is a power law. Now the exponent has a significance, and the question answer you want to ask furthermore is that exponent a universal type of thing, or that exponent varies with the type of climate that you have? Because the question is valid, because we know the networks, regardless of how different they look to the eye, they do have an intrinsic unity in all of them. I can tell you that all of them have some principles on it. And all of them have some characteristics in the network which are the same. I don't care if the network is in Cantabria, in Venezuela, or in South Africa. So the question can be related to the species, and it's still something that has to be studied. And then you come and say, all right, let me try to link the structure of the network, in which I am not going to detail how, but we know, take for granted for me for a moment, please, that one can describe mathematically, how many of these are there, what is the probability that one of these is linked to another one, et cetera, by very neat type of equations. Regardless of how they look, those things are general. And you say, all right, let me start something which is called a meta-community model, in which in every extreme link, in every one of these, I have a community of species. And then mathematically, I will illustrate what is done mathematically here. You can say, all right, these are the species that were living there, let me kill one. So I open an empty space for whatever reason, is competition, for whatever reason it is, and that's the way you do it. And then you say, all right, every individual now in the system has the same probability, the same probability of dying. So let's say that this one dies right there. And then with probability nu, a new species from outside, that's a speciation, comes and replaces that. You have a pool species from outside. And then you can say, okay, but also with probability 1 minus nu, the empty spot can be colonized by any individual from the other side. Say I choose that one at random, and then you say, aha, there it goes, and then you go, no, there is, and it will colonize that space. Now that seems, hey, that's complicated to do. No, it's not that complicated to do mathematically speaking, if you know what is the structure of the network, and if you know how to play a little bit with probabilities. So we can do that, and that's exactly what we did. And then we repeat that until the process reaches steady state. I will not get into what is called neutral models and things like that, but the thing is that at the end of the day, you get a very simple model, simple because it is related to unifying type of properties in the network, and you say, okay, let me try to apply that model to something really big. Let's dream the Mississippi River Basin. Why the Mississippi River Basin? Why? Because first, it's big. Second, has wonderful data in terms of fish diversity. And thirdly, it spans a lot of climatic type of conditions. And then you say, all right, this is, credit is you, that was part of the thesis of Rashata, Shotman, and Parakul, published in Nature. And then you say, aha, this is the data analysis that we have. In every one of those black spots there, we have data about the number of species. Nice data, huh? Well, in fact, it was the same thing that we did for the Mekong. Very similar was the model that we did for the Mekong River Basin, very recently on that one. And then then you say, okay, what do we want to describe with the model? We want to describe biodiversity. Biodiversity is just a word. There are 3 fundamental types of biodiversities. You see, you have this network here, schematic here, 1 and 2. And in total biodiversity, they have, they have ABC, 3 different species, but they look very different. So you have what is called local biodiversity, in which this one, okay, is larger than this. You can see in the average on every link has more species than this one. You have total biodiversity, in which is the same, ABC, ABC. And between community diversity, I mean the changes in biodiversity from one link to another on the average is larger in here than in here. There are more common species here. All here are contained here. so the between community biodiversity, which is all beta biodiversity, is larger in case 1 than in case 2. Sorry, it's larger in case 2 than in case 1. So we do that. We run the experiment for the Mississippi River Basin. And this is the so-called alpha diversity profile, meaning the local diversity. This is local species richness up right here. And you have the number of species. And this is topological distance to the outlet, number of links in the network. Rather than use kilometers, it's much more general, elegant, and beautiful to use link topological thing, because that takes the quantity itself, immediately convey the idea is, I don't care if it's large or small. I don't care if a tree is large or small for its topological description. The type of mathematics that it uses is the same. And then in here you see very pretty how the points, the red dots, are the actual data. There is no fudging here. There is no fitting of the thing. And here is this, the model. And you say, oh, here is not doing very well. That's New Orleans. And the reason why we speculate it's not doing very well there is because in here, in the New Orleans area, not so much of the man-made type of disturbances that could play a role also, but there are a lot of invasive species from the sea. The water there is not anymore fresh, really. So in here, in fact, I am glad the model did not do well in that area. Now, this is the alpha diversity histogram, very nicely reproduced. This is the between diversity, very beautifully reproduced. And this is the species range, meaning the more common species, rank 1, the less common species, and the number of links they occupy. And then the model reproduces whatever you want. This fundamental, a little bit of change. That model was the one that we also used for the Mekong for a very practical type of thing. Now, you want to look at how the model does kind of reproduce different. These are the 5 or 6 more common species. And one is the model, and the other is the data. So it's doing well. So how can you use this model? Oh, you can use this model, as I said before, like we used it for the Mekong, to say, I change the connectivity because I'm going to put 50 dams, or in fact, of that order, to develop the river system in terms of hydroelectric type of energy production. So that's going to change your connectivity dramatically. It's going to change also your habitat capacities, et cetera, et cetera. It can be done. It was done, has been done at least for one place, and it has been very much commented in different, because some people like the results for some areas, and some people, because at the end of the day, we ended up saying, these ones and this one are really dramatic. If you build those ones, we're not in the mainstream, in fact, in the case of the Mekong, where some tributary dams, they want to say, those will impact dramatically the biodiversity and the total biomass of fisheries in the river basin. As then, a lot of people more in the conservation side, blah, 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 very good, very good, very good. On the other hand, we say, these ones and this one do not play a role. So people need the energy. If you have to do something, go ahead with them. Then the other people say, ha, 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 but you cannot please everybody in this world, I guess. Now, you can also ask the question about tree biodiversity. It's a different type of thing. I talk about the riparian areas, but you could talk about science questions like, can we model vegetation, patterns of vegetation diversity? And again, if you look at the Mississippi River Basin, we have some wonderful data, which were over 34,000 plots the Forest Service of the United States had, plots of 30 meters by 30 meters, in which every species is determined and every species is counted, and the number of individuals of every species is counted. So there are 34,000 of them. It's over 178, but we were considering 178 species, and this is the river basin again. And you say, okay, how are they connected? And again, I don't have the time to go in detail over it, but you see, we can again reproduce the alpha diversity, the beta diversity, the gamma diversity very, very well. Now we are talking about trees. And then we are going to do the following. We want to study here the impact, possible impact of climate change in the in the tree biodiversity, not only forest, the tree biodiversity in the Mississippi River Basin. And we are using here, the key of this is to map here the mean annual precipitation, and this is the forest cover. And the idea here is to say, okay, the mean annual precipitation controls if you put, these are the different plots that you have in there, okay? And then you say, all right, there seems to be a mean annual precipitation above which, you have 100% of forest cover. And then it starts decreasing. This is an envelope of it. What climate change will do Many things will do, but one of the things we'll do is move this mean annual precipitation lower, so you diminish the habitat capacity of the area, which is one of the fundamental variables of the model, and then you can study, I have to rush, the macroecological biodiversity patterns, and again, this now is vegetation, and the model does very well. Interesting enough, let me go over this relatively quickly, then you can say, hey, let me put now different scenarios of climate change. There are 15 climate models, you know that, different emission paths, et cetera, et cetera. And what are they going to change? Well, I will not get into the details of this, but in here, let me simplify the issue for a moment. I believe that one of the greatest impacts of climate change is going to be not from the hydrology point of view. People talk about many things. It's going to be in the dynamic of precipitation. And it's not only mean annual rainfall, which is the one I will be focusing here, but also how that mean annual rainfall takes place, you see. It's very different the way it works, a tree from a grass. A tree has long roots, deep roots. A grass has, I always say that the trees are very much the Anglo-Saxon type of living beings in a forest, and the grasses are very much the Latin type of things, you know. The trees are there with their long roots to take advantage. They plant in the long range. No, it rains, and they accumulate that thing, and they transpire with a certain rhythm, et cetera, et cetera. The grasses, they have short leaves. When it rains, they have to use that rain very quickly because the damn thing goes to the roots and go back, and they cannot use it anymore. So they are much more in the Latin spirit to hell with the future, you know. No, we enjoy it. We transpire like crazy, okay? These are two very different types of strategies, the one of the grasses and the ones of the trees. But with the same type of annual rainfall, you can have more storms or less storm, more storms, less intense, less storm, more intense. And that's very, very, very different dynamics, which will impact dramatically the type of vegetation that you have. That we have studied in detail. That needs more study, but it's very clear. It can be done, and it has been done. And it's a very exciting field to get in. In this case, let me just go over some details here. We just put mean annual precipitation. I'm not going to show results of the actual dynamics in terms of the rate of arrivals of the storms and the depth of the storm, which are a stochastic process. Both of them is a market Poisson process to those that are a little bit more involved with statistics. And what we do is say, the scenario of climate change moves the mean annual precipitation, so it changes the habitat capacity. And then I can, let me skip this one, I can study how the alpha, beta, and gamma biodiversity change under different scenarios. And this is just an example of a scenario. And you see red and the blue things. And this is the total Mississippi, Missouri River Basin. This is the north area, and this is south area. And then you see immediately the blue one is the histograms, the discrete thing is the actual data. The blue one is the model for that. And the red one is under the scenario, one of the many scenarios of climate change. And you immediately see how, for example, the occupancy versus rank goes down. We lose species, especially those which are the rare species, okay? The one that have a high rank. We lose considerably here. This is in the north part, also in the total river basin. And here, again, if you look at these, the distribution moves towards the left. Measuring quantitatively the impact, let me skip this, of climate change on this thing. Very, very fast, and let me talk in wetland, touching wet, 3 minutes? Okay, thank you. In wetlands, which is a topic very dear to my heart because wetlands are beautiful, mainly because of that also. I mean, they are very useful, you know, all the ecological system. They are the filters of many things in nature, et cetera, et cetera. But this is the Everglades. And, you know, one of the things that drives biodiversity in wetlands, in my opinion, the thing that drives biodiversity in the wetlands and controls the spatial structure of vegetation in wetlands is the hydroperiod. And this is nothing new. People talk about hydroperiod and say, hydroperiod, you have a hydroperiod whenever the water is on top of the land. You have a wetland. Okay, it can be dry or can the water be above. But that doesn't help at all. Huh? If you're going to do science, you have to be quantitative about it. So a hydroperiod at least involves three different things. It's how frequently in any given spot the water is above the land. It can be all the time. It can be very, very few times. How frequently it is. How long does it last, the water above the land? How deep it is. All those three variables are stochastic variables, are random variables. All of those three variables can be quantitatively described. And all those three variables will impact the spatial distribution of vegetation. And let me just describe very quickly in a minute and a half. This is the Everglades National Park. We have data, very good data in the Everglades, have been studied to death, of 20 meters by 20 meters number of type of species and number of different type of things. We have, I think, 87 type of different, well, you could say not really species, almost, different, are almost species, almost. I mean, it's much more than just functional types of vegetation in the case of this data. And just to give you an idea, for example, this is, look at this guy. This is the, let me see, this is the sawgrass, a very common guy. The sawgrass doesn't care. Let's take this one. Percent of time the land is inundated. And you go through all the pixels in there. These are percentages type of things. And sawgrass seems to live beautifully well in all of them. But you take this, the mulligrass, a different type of grass, and only seems to live nicely when the percent time of inundated is relatively scarce. Or you take this other one, which is the bay hardwood scrub, and it only lives nicely in those areas which are most of the time are inundated. So you can go like that to different type of species, and you can relate them, the species with the hydroperiod. And then you can ask yourself the following question. I want to study the impact of climate change. Fine. What is climate change going to do for me? Well, it's going to impact my species, but how? Through the hydroperiod. So the question is, if you give me a change in the dynamics of precipitation in which you have two fundamental variables, how frequently the storms arrive and how much water comes per storm. Both are random variables, okay? But you can describe them relatively easily. We know how to do that, okay? And you say, okay, with those two parameters, can I describe the probability of how long will the water be, how probable it is that the water will be in any particular spot above the land? That's the percent of time the hydroperiod will be present in that particular spot. We can do that. And then we can say for different scenarios of climate change, how the percent of time changes from the present situation to the situation of climate change. And then we can play different scenarios of climate change. We can also talk about the depth of the water, et cetera, but just concentrate for the time being in percent of time of water above the ground. And this is just an example, okay? In this case, I think I will finish with this. This is an interesting case. This is a probability distribution that water is above the ground, okay, in a particular site of the Everglades. And now, in this one are the observed data, and this is a mathematical model done, not fitting, I mean, taking into account the dynamics of the rainfall, the water table coming up, et cetera, et cetera. Fine, it does well. But now, I'm interested in showing you this one. In here, we left the total amount of rainfall the same. The only what we changed was we made lambda 10% lower. Lambda is the rate of arrivals of a storm, meaning in here, the number of storms that contribute to the annual precipitation is 10% on the average, because it's throughout the year, 10% smaller than the other case, 0.9, the rate of arrivals. But the mean annual precipitation is the same. Therefore, we have to increase, in a correlated manner, the average depth of rainfall. So this case here has fewer number of storms with more depth of rainfall per storm in a random type of modeling, okay? And we do that. Look at the change, 10%, you say, that's not a heck of a lot. The impact on the hydroperiod structures of the Everglades is dramatic. This distribution, the blue one, comes like this, okay? And that, in fact, immediately impacts the spatial distribution of different type of vegetation, as we saw on the slide before. This is the way to really start trying to bring up the quantitative part, I mean, to be objective about the impact of climate change in issues like biodiversity, which are crucial for sustainable development. But they have to be focused, first, with a very open mind, and secondly, with a clear vision of what are you trying to do. What are the parameters? What are the factors in the dynamics that control the process? In the case of rivers, connectivity. In the case of among other things, in the case of fish, connectivity. In the case of wetlands, timeout. In the wetlands are hydroperiods. That's a hydrologic factor again. Huh? Hydrology is ruling the system, but in a very different manner. And then you go in and try to describe what is going on in a general fashion. In the case of the river, using the structure of the network as the general tool in which we know quite a bit of what are the general structures of the river network, regardless of how different they look. They have some unity, fundamental unity behind it. In the case of wetlands, hydroperiods by themselves. And that's the way to go. Believe me, for the young people, it's an exciting thing to do. It's something that, you care a lot about doing it. There's nothing comparable professionally to the feeling that you have one night, late at night, when you say, my Lord is working. Dios mío, que está dándole bien. That is the moment, okay? And when you smile or you see the graduate student smile and say, I got it right, that's what we live for. Thank you very, very much to all of you again, okay?